Thank you, sir. So before we start, let me introduce about our speaker, Professor Amit Seth. Professor Amit Seth is an educator, researcher, and entrepreneur. He founded the university-wide AI Institute at the University of South Carolina, AIISC, and grew it to nearly 50 AI researchers in 4 years. He is a fellow of IEEE, AAAI, AAAS, ACM, and AIAA. He has co-founded 4 companies and ran 2 of them. This includes Tally, which is pioneered semantic search, is a DI, which supported knowledge infused clinical NLP and NLU, and Cognovi Labs, an emotional AI company. He has advised and mentored over 45 PhD and postdocs. If anyone have questions, you can raise the hand by clicking on the button below and we will unmute you. Also, you can use the chat section for any questions. So you can start sharing the screen.
What happened?
So below there is a share button. You can click on that.
No, I did share. Hold on a second. Something is. Ah, okay. Thank you for your invitation. I've in the Vita or in the brief bio, I forgot to add that I'm a proud alumnus of BITS Pilani. I was in the 7681 batch and did triple E. I don't think we had computer science degree at that time. So I was 76 triple E 056. That was my ID. And glad to you know talk to BITS audience. I did have an opportunity to visit AppCare some time ago, and glad that you asked me to share some thoughts. So, briefly about the AI Institute, we are nearly 50 researchers, and we do quite a bit of activities in the AI. Both we work on core AI topics. Today, I'm going to talk about knowledge infused learning, or a particular NeuroSymbolic or hybrid AI. We have another fast emerging area of working on compact and custom models, language models that also bring in the NeuroSymbolic ideas. And then there are, you can see a lot of other topics that we work on. Another important thing that we do is to uh, do do applied or translational work. In that, a lot of our challenging, um, research ideas are rooted in real world requirements. So many of our most of our work is team effort, and in many cases the teams span us in computer science and AI with people in various domains, and you can see broad variety of other domains that we work on. The advantage of this is that we would often have access to real world data. For example, in smart manufacturing, we have access to collaborators who actually run assembly line and have sensors, and so we have data that are collected for our own research that goes with all the other topics that we are talking about here. So in most of the case, well, of course, it is wonderful to have open data which we use. We have to do that, for example, in social media data. But in many other cases, we have unique data that comes from, let's say, electronic medical records or fMRI brain images of the brain. So those are the, that adds to the richness of the work we do. There is in fact we also have a lot of collaboration with industry. There's a project funded by Wipro that is in the pharma area, and a whole number of local, national, and international organizations or companies are collaborators. Today, I will talk about the evolution of AI as from one particular perspective. And the important, and the main thing that I want to do is to discuss the, promise of NeuroSymbolic AI, and three very important topics that have emerged more recently: alignment, grounding, and instructability. And then I'll discuss some examples. Um, At a very broad level, if you step back, we have seen three waves of AI. There was AI of the last century, before the so-called AI winter, and there we developed hand-coded knowledge and tried to utilize that. Then the AI that most of you are well aware of, the AI of, including the generative AI revolution, starting with the machine learning, deep learning, and now generative AI. These are the key terms that have emerged, and all of you are aware of LLMs and ChatGPT and such. And and we are probably at the peak of that, wave, and there is an emergence of a new wave, which is a third wave of AI. And this wave may be called hybrid AI or neurosymbolic AI or all of that. And DARPA called it, one that focuses on explanation and being able to understand what AI does. So in the current generative AI, the systems are black boxes by and large, and thus we don't know exactly how they came to a decision, and that has many implications on their use. So we started with this, formal AI. There was uh, logic was a very important part of that. There was, within those contexts, there was, good understanding that we could do a variety of reasonings: deductive reasoning, inductive reasoning, abductive reasoning. There are other types of reasoning that have also, emerged, causal and analogical and such. But these were very, these were discussed heavily in the last century. Um, and then, well, there are certain advantage of this reasoning, this verifiable, consistent, interpretable. But, there are also things that can happen with these systems where you can reach wrong conclusion. This example of duck and duck is, ducks are real, but the duck is that real or not real? So in that sense, there are some challenges with this type of reasoning. Um, then there emerged the role of knowledge engineers and capturing the knowledge. I remember developing an expert system in 1987 for the uh, aircraft landing gear, nickel chrome painting of aircraft landing gear. So there are a bunch of rules about what could lead to a problem with the uh, plating, nickel chromium plating, and how do you resolve them? How do you identify them? How do you avoid them? So I hand coded a lot of knowledge necessary. I had to get the knowledge from reading books or getting from the experts, and then we developed an expert system. Um, uh, then came the development of kind of knowledge graphs, or earlier these were called ontologies, WorldModel, and such. And they with that you had further advances, and this was an era where semantic web and enterprise knowledge graph and other kind of techniques and technologies took shape. Semantic web, I think the term introduced around 1998 or 99, became a significant area of computer science in the first decade of this century. Um, and then came the neural networks, and so came the in 2000, and so first came machine learning, and that was very well practiced quite a bit in the first decade of this century. And then starting 2012 or so, we started, so that is just about 12 years ago. It's not that long ago. And now, in this particular case, one thing that happened is that uh, the machines, we were able to use machines to process and learn from very large amount of data. And that had several advantages, and many of them are seen in the generative AI systems that we know of today. But they still have quite a bit of limitations. These are not verifiable. They take immense resource. It costs, uh, you know, 3 cents for 1,000 tokens for, if you want to use GPT. So the amount of resource that we use for training this model, is massive. And don't so let's not forget that all of these results come at a significant cost. Many companies cannot afford, in fact, to use commercial versions of the systems which are the best right now compared to the open source systems. Now, there is also they claim that we uh, can do some they can do some reasoning, but I think that reasoning is very, very limited. And the general strategy is to construct a benchmark with the reasoning problems and see what happens. And that the reasoning is never comprehensive. So if you can show some incremental improvements on the benchmark, and say, okay, we are learning to do reasoning. So reasoning verification strategy is purely empirical and unprincipled. Uh, there are techniques like chain of thoughts, relational, rational engineering, prompt engineering, others in context learning strategy, but they've shown only modest improvement on the reasoning benchmark. And also, uh, that is also in the context of using a system that are very large. So this capability can't be shown very well with the smaller models. You need very large comprehensive models with substantial resources spent for developing them. And there you started to show some value. This, at least for now, doesn't appear to be a very sustainable strategy. So with that, we started, working on NeuroSymbolic AI, and there are two, three major approaches to NeuroSymbolic AI. The symbolic part is what we discuss, the AI of the previous century, and formal systems. The neuro are the statistical systems that I discuss next. But people realize that what if you combine, ask what if you combine the both of them, and can we get power from both of them? People started noticing that data alone is not enough. In my second company that I started, called Tali, which became Symagics, And so I started that company in 1999. I developed, my team developed both statistical classifiers and a knowledge base classifier. So we developed a comprehensive knowledge graph or world model of all these different domains: entertainment domain, sports domain, news domain, politics, and so on and so forth. And then this was 12, 13 years before Google also came up with knowledge graph, Google knowledge graph, which is now integral part of Google semantic search. So Google's earlier search was not semantic, and then I suppose the audience, most in the audience, in this audience, don't know about the previous version of Google. But that was that they did employ machine learning, but Google also figured out, as I did 13 or 14 years ago, that you need both the knowledge and the machine learning to get better results. And so you see all this info box on the right hand side for the search results. We had already developed that at the turn of the century. But a point here is that basically people realize that data alone is not enough, and that just you need to add knowledge to the mix. And knowledge is often available in many forms, so why not use that? But how do you effectively integrate a data-driven system with knowledge is a challenge. So if you have read what I've said here, is that this is from our paper, a short paper, article actually, that this is a more of another way of thinking about it. There is a very influential piece of work, or there's a book called as we no the book that was called that talks about system 1 and system 2. And this was coined by Daniel Kahneman, who just passed away, I think, a week ago. And he got a Nobel Prize in economics for that, so behavioral economics. And the system 1 is what you might call a system that engages in perception, and this is very fast decision making. So you can, at a very high level, you can say that the statistical systems that we have built are ones that can support perception, very quickly analyze the data, answer a query. And then there is another part of our decision making, our thought process, the way our brain works, that is around cognitive capabilities. That is deliberative, also called system 2. So and this would be more aligned with formal reasoning, or with supporting variety of reasoning, and deliberative thought process, and so on and so forth. So at a very high level, with the neurosymbolic system, we are trying to combine both of these part, the perception kind of things with the neural network based processing, and the cognitive part with more of a symbolic AI kind of system. And what ties them together is the knowledge. They play critical role in connecting. Your eyes sent you, your senses send you 11 million bits per second to your brain, and your brain forms thoughts, and those thoughts can be well aligned with the knowledge that you have. Each of us as humans have our knowledge and experiences, and all the data that comes to our brain is processed through the intermediated by knowledge and experience. And it's not just that data is somehow processed and we can understand it, no? So by and large, the neural network based processing, for example, can do excellent natural language processing, like natural language translation, but they don't have much of a natural language understanding. So to ground that processing, you need that knowledge, and that is what leads to understanding. So there are a broad variety of systems that then have started to evolve in the NeuroSymbolic AI space, and this is one of several possible taxonomies. So there are different ways that symbolic uh, and neural network based systems that get combined, and in this, you're welcome to look up the paper if you want to go more. You'll see that a broad categorization is on the left, and then the strategy or method are described here in the middle, and on right hand side specific techniques and the systems that have followed those techniques are there. So you can look up how each of these systems have been done. For example, K adapter or TDLR, or PKIL, or variety of different systems that have developed, or your combined ChatGPT with Wolfram, or your LangChain pipeline. All of these variety of things somehow use incorporate knowledge in addition to statistical processing or neural network based processing. And uh, so while I won't discuss all of this in great detail, I'll give you a quick summary of these things. So there is a generic architecture we put together in that article, which involves you know data and knowledge graph and knowledge sources on the left, and then variety of kind of processing feature, abstraction layer on working on your neural networks, and then there is neural reasoning that you can do. On the bottom you see you are doing knowledge processing and understanding, and then you may have workflow and process guided reasoning. uh, uh, Andrew Yang just gave a talk, I think last week or this week, where he talks about workflow of agents. So now um, I'll make further remarks towards the end of my talk. But you have options, instead of developing a taking a common crawl and every data that you can sweep off internet, and then training your very large model, like the ones of GPT or Llama or others. You can uh, think about breaking the problem down in variety of areas and make specialized systems or agents, and then bring them together, coordinated, use them in with some level of coordination. It reminds me of the work that I used to do 20 and 30 years ago. In 1991, I started a project on distributed workflow, and we used to talk about a dynamic workflow and adaptable workflow, and the workflow had tasks or steps. Now replace those tasks or steps by these modern agents that can be specialized models, AI models. And we used to discuss how you can get a activity done, let's say product development or a service request, using multiple of them. So now people are also thinking of that architecture, and I think in the next 5 years you'll see a lot more growth in that area, um, while the big model era kind of has already reached the peak. So, in the simplest of this method, what we call as knowledge graph compression, what happens is that you bring the knowledge. Now, there is a lot of sources of knowledge, right? You have something like Wikipedia, and Wikipedia or Wikidata, can be represented as a graph. Because you can extract that as a DBpedia, let's say, from Wikipedia. Or there are other hand-developed knowledge graphs. There are techniques. For example, my group has developed a tool called Empower that takes structured, semi-structured, and unstructured data sources to create large knowledge graphs much more efficiently than before. And that that knowledge is created. It can be segmented into sub-regions and sub-areas, and then you basically do the embedding method, take the embedding route, where you essentially are taking the knowledge and getting into the same form as vectors. So ultimately, you have everything in the vectors, and you can do this multi-tier, multi-layer processing. This brings some value. It has shown 10% or around that kind of improvement to several tasks, um, and it is relatively easy to implement. Because ultimately the computational mechanism is not changing much. You are taking the vectors and combining them. So while it is less manual or less effort, it also, the improvements is also modest, and you lose uh, details as you convert the knowledge graph, which is in a richer representation format, as a graph, entities and relationship and types of relationships and hierarchies and all that. Those that richness is lost to some level when you kind of do the embedding. But a lot of early systems did that. Um, you may also try to do the uh, processing where, after doing neural network based processing, you use knowledge, and you use the forms in which you know how to query and manipulate the knowledge, such as Sparkle. So your graph may be RDF, and you may do a Sparkle query, and essentially uh, do a post processing of what comes from the neural net processing, and thereby it can do filtering of some sort. It can do ranking of sorts and such. So in that sense, adding the knowledge, post hoc, could be also of value. You can try to connect what you got from neural network to the knowledge graph and then give the results. But this has also some advantage, but got a lot of limitations. I also want you to kind of understand that it's important to that there are broad class of applications. So very often we pay a lot of attention to search or question answering or recommendation. And when you work with a digital assistant, for example, you ask a question and you get a response. But what happens is that these systems don't typically retain context too well. So take the example of developing a system that helps you improve and maintain good mental health, right? So you suppose we are developing an AI agent, or a co-pilot or something where the agent interacts with the human to uh, daily understand how the human is doing, how the patient is doing, and give the recommendation or suggestions subject to some medical knowledge and constraints. Now, this has to happen for many, many days and years, maybe, right? So, our current digital assistants don't maintain this context. They are not highly personalized to understand you, what has happened. They are not personalized to, they're not developed to ensure that medical knowledge is appropriately applied. They are not developed to make sure that the communication between this agent and human or patient does not cause harm to the patient. So there are broad class of applications uh, for which the current most popular form of the AI that we all think about, the generative AI systems, they are not the ideal way to support them. So there is a lot more of AI that is still needed to be developed, and we will come to that somewhat later on. So you may this is a variation thereof, and you may essentially say that it will be good to solve the problem wherever I can apply the knowledge, but where I can't, let me use my backup of using the neural net, because the interesting thing is that if you ask something to a large language model, a question, uh, either it will, in many cases, um, at least the early versions of this would almost always come up with the answer, and in many cases it will make up the answer. So the so-called the phenomena of hallucination. Nowadays there are some guardrails that are developed, and there are more and more of those guardrails. So there are certain topics, for example, some of these language models would not converse with you if it involves, let's say, health, because they know that talking about health with they know that they either lie at times, or they are wrong, plain wrong at times. So to prevent, or that such a thing could hurt human or users, so they put those guardrails, but these guardrails are very flimsy, very ad hoc. Today you report on some problem, and they, and quite likely humans sitting back looking at failures are fixing it, right? And they're putting rules saying don't talk about this if this subject, let's say discussion about suicide, is something we will not allow or support, or stock guidance we could not, because they know the limitations of the systems. Now when you so that is one issue to keep in mind. The other issue is what I already brought out, saying that there are class of applications that are long running, where you have to maintain context over the long period of time. These are the systems that we can't do too well today. One of the techniques that we have been trying out now, so first set of techniques that we were interested in were in knowledge infusion. The knowledge infusion is that you have knowledge that you somehow enrich the neural network based processing, which is typically known to be more scalable. How do you enrich that with knowledge, so that that grounding in the knowledge yields better result, right? And there are many reasons the knowledge works and does what it does for improve to improve the system. It could be that knowledge has information that complements what is can be learned from data, right? The data just does not have that. Or that it may be that knowledge has you know um, correct way of how one object or entity is connected to another entity. That kind of specific thing is not available in the through from a neural network. So because the whole system of language model is about predicting the next word, right? And in fact, there is a lot of things done for that yield that allows very high scalability. But when you say take a word and tokenize it, a lot of things, even the linguistic knowledge, may be lost, right? If you take natural language as its own, you can see where the comma is. You can see, and the change of the comma, where the comma is, changes the meaning, right? And so we humans, when we do natural language processing, we are using a linguistic knowledge. We are using lexical knowledge, rather. You're using lexical knowledge and you're using linguistic knowledge. That by itself, these systems don't, can't do. Somehow these things are reconstructed, and clearly these models learn exceptionally well the task of language generation, no doubt about it. But that deconstruction of the language it reads, the data it processes, unstructured data, and the construction, again back to the um, uh, you know um, language as good as humans create, or most humans create, not all. Experts still do better than these language models. uh, has inherent, the compromises are done that inherently loses out on number of things. So if you look deep into that, those also lead to why there is hallucination, why the systems make up the facts, or makes up information that is not factual. Uh, so in any case, we first number of people, including my group, did a variety of things for knowledge infusion. Now we are looking at the reverse process, saying, could we elicit knowledge from the language model and then connect with the symbolic part of it, the knowledge graph part of it, and create a contextualized subgraph that can then give answer to the question. There are many issues now about the efficiency, the quality, but at least this particular path would be more flexible, open-ended, will be able to amenable to use of the world model, meaning the all the factual things you have, such as the things in Wikipedia or Wikidata or such, and that because the latter part is done within this symbolic context, there is a you can find a path, you can do all kind of operations that you do with graphs, that it is interpretable and so on and so forth. So that is another option that you have. You get the benefit of having learned from the data, which is very important, which is what the neural network does very well. So with the NeuroSymbolic AI, we leverage both data and knowledge in systems that are conformant to the world model, meaning as humans, we process the data and we have our knowledge. We know that New Delhi is the capital of India, and several things that specifically that way. Here also the system knows is verifiable, constrained, consistent, and so on and so forth. It's interpretable, and such. So what we are with this NeuroSymbolic AI systems that are centered on use of knowledge, we use explicit world model, we have verifiable reasoning, and you can interact with the system or use domain constraints. And there are three very important terms that you will hear more and more about if you not heard them. One is the alignment, meaning the system behaviors are in accordance with the end user expectation. Today, can you tell whether the concept, what you had in mind when you formulate a prompt or query is what the system understands? It's not the case currently. It's not that system and the user are on the same platform, on the same they are not actually. Systems is a system is very dumb in one sense, in the sense that it never has to truly understand what the human means. Alignment means there is for system to understand what human means, you need a knowledge as a common item between user and the system to get that. Second is grounding, in that the concepts are grounded in the concepts in the real world. So you have the knowledge of the world, and whether it is the factual world model, or it is domain specific like UMLS or variety of other medical knowledge graphs. There is something in the system AI model that can be mapped to what humans understand, what is part of the knowledge. And instructability is that ability to guide the system to incorporate additional context and constraint. For example, in AI system, an agent is talking to a patient, but the doctor is watching out in a way that if necessary, it can give the instruction to change. For example, I have a system that looks after an asthma patient, and it's meant to support a person with low level of asthma. But if the system recognizes that it is now requiring, the severity of asthma is increased, it is possible for just like you go to doctor and doctor changes the medication or adds more stronger medication, Those things you should be able to tell the model, and model should adapt to the new circumstances. And you don't a patient does not change medication on his own. A patient goes to the doctor, and then the doctor considers variety of things and then changes the protocol. The same thing here, the doctor should be able to, expert should be able to change the behavior of the system. That's where instructability is very important. So there are a number of examples that uh, uh, that we can use and that we work on, that demand this kind of next generation of systems. In the in US, I mean, throughout the world, there is a huge um, growth and increase in the mental health problem, and this is particularly seen after the COVID. So there was a 40% increase in mental health problem in the US, especially among adolescents and young youth. And there have been there are mandates, in this case government mandates, that for every mm, 350 students there should be one mental health counselor. So to take care of a whole variety of issues that occur in the classroom and student behavior and student health. But that is not possible because there are not enough healthcare workers and counselors, trained people that can act as counselor. So there was a ratio in my state here in South Carolina of 1,300 student per counselor. That is now decreased to say 900 students per counselor, and it's further going down. But the mandate is to have one for every 325 students or 350 students. And when you have to take care of so many students, you really need a lot more efficiency, and the current way of total manual taking care of the students in manual operations is not sustainable. So how do you develop technology that would support that? So in this particular case, this MTSS system has classified into 3 tiers of service: universal, that can be offered at a very broad scale, at a class level, school level; targeted, it's also called tier 2. Universal is called tier 1, the targeted called tier 2. And there are certain kinds of things like behavioral counseling where a group of students are assigned to. And intensive, or called tier 3, which is done one-on-one. And there is a particular structure, structure in this case involving students, school staff, school level team for mental health, shown here in kind of pink, and district level team. Schools are part of a district here in US most of the time in public school systems. So a school system district may have 10, 15 schools. So and the budgets are at the district level and such. So this group of these teams of experts have to work together to support all these students, and that is what MTSS is about, although we will not discuss in a lot more detail here. um, and in the course of supporting the students, there is a combination that happens. So here you see the in blue the school level team member, these are counselors, and yellow you see a district level team member. District level is higher level than school level, and there is a communication that goes on, saying John, the student, um, is part of Mr. A's anger management class. But then there is a protocol saying, oh, if the student is less than 17 years old, then an MD must be present. But then this this person says, we don't have budget for the MD. And then there is the school district level guy comes back and say, okay, I can manage that, I'll arrange for the budget, and you can go ahead with the service. Right? So these kind of interactions are happening. Now what has to happen in this process is for AI model or AI system to assist these people. That is how you'll make it efficient, productive, consistent, reliable, and many other things that we want to have these neurosymbolic AI systems to have. So you can see here in the communication, there is a role of what we call as deductive reasoning from the protocol, deductive reasoning from the protocol plus inductive reasoning from data, and then retrieval augmented abductive reasoning, right? So there's a different class of reasoning that are necessary in supporting. And what I'm saying is that now your agent needs to be able to perform this type of reasoning to support um, this activity. And if you now start asking your generative AI based assistant of today, they are not capable of doing this kind of support. Now in this context, there is a grounding that happens. You can see that the concepts like student or issue or class, these are all grounded in the model, right? That way what what is in the natural language here is understood by the system, by the AI model. There is because they share this model, and the concept in the that is in the natural language are grounded into these concepts in the world model. And there's a role of instructability here, where you can see in the gray there is a controller co-pilot. A co-pilot is a so there are three interesting related concepts. One is called the chatbot, where you ask a question, they'll answer. Other is co-pilot, where this will help a human, but there is a human role. It's not entirely on its own like chatbot is. And then there is agent, which is all its own, and it is autonomous, and it makes a decision on its own. So there are many tasks where we would not be comfortable for the system to work in isolation or autonomously, and that there should be an expert in the in the mix. So here there is a school level person in the mix, there is a finance person in the mix, there is a district level person in the mix, and they are all able to talk the language that the AI system understands, and that you are going to be able to use the data that is available for the user. End user is the student here. And then all the things that you learn from large amount of past documentation, and you have the protocols that are specified, and so on and so forth. So what we see now is a set of systems that are evolving, where you are going to combine both the kind of reasoning that used to be possible, or that for which the formal systems and symbolic systems are good at, and the neural network based systems and the data driven systems that the second generation of AI is so good at. So together we can develop more powerful system. There is another example here, of mental health agent that we have developed, and you can go to our web page, and there is a let's see, I'll just give you a snippet of this. Okay, I don't see voice being played, so I don't know why that is the case. Okay, so I can just talk. But here there is a architecture, but what's happening here is interesting, that there is a communication going on, and on the right hand side you are seeing that there is a user knowledge graph, and there is a other knowledge that are available. So all the communication is being instantiated in the context of this knowledge. So you know exactly what is happening, and various medical rules. For example, you have medical protocols or guideline. There's something called clinical practice guideline. When you go to doctor, doctors are trained in saying, how do I diagnose this disease, let's say blood pressure, and what class of medication I should use for this particular patient. They're not arbitrarily just coming up with something. And so they follow specific sets of reasoning. This after that, if this is not the case, then it may be this one, get this new lab report, and so on and so forth. So here, that kind of reasoning can be seen on the right hand side. That kind of deliberative, uh, and then the communication is one that is the whole interaction is done that is within the realm of what a doctor would do. And there is also a number of things that happen. Let me show you one or two more other things. This is a more detailed description of the chatbot and how sorry the how these virtual assistants develop. But I want to show you one more thing. So what would happen here is that you see on the left hand side here is a communication using a state of the art language model. And In this language model that has been trained with also some of the medical knowledge, it comes up with this question to the patient, that do you feel elated or self-destructive? It so happens that that will be a wrong thing to do for the particular this patient, for the class of mental health that patient suffers from. Asking self, are you self-destructive, would cause negative thoughts and could hurt the patient. So you need to have incorporated the medical knowledge, and you have to do this safety check such that you will take out the self-destructive part of the question, so that and make it safe, right? These are very important things. So before you can fill this, if you had just created a chatbot that is purely data driven, even if the data that was fed in there was had some medical knowledge, it would not have understood when to apply that knowledge. And the NeuroSymbolic AI system would be able to understand in the context in which that particular knowledge will apply, so as not to ask about being self-destructive. And so there's a paper that discusses that in more detail. The other thing is being able to explain. See, a doctor cannot just, if the doctor, at least in US, has to be able to record why he or she is recommending what it is. Just because an AI model tells you to do something, he cannot blindly accept that. Otherwise, you will be doing medical malpractice or subject to legal action and other things. So the doctor has to understand why has this AI system or AI model suggested what it has suggested. Well, to be able to do that, you have to make the system explainable. So here I'm showing you a text here, and I'm showing you how this text gets, there are concepts in the text which are in, bold brown text, like bisexuality, chaos in my relationship. They get mapped into the specific concepts, medical concepts. In this case, these are the concepts coming from DSM-5. The what that is used by medical professionals. And then there are definitions like OCD is XYZ. So you are making sure that this is classified as OCD. You can develop a system that says this is OCD, but if it cannot explain, this system would be not usable for medical professionals. This is what is necessary, and probably all of you know that these generative AI systems are not very explainable, or in fact not explainable at all. Anyway, so now ending up more or less, one or two last thoughts. Humans are guided by and subjected to law, regulations, policy, guidelines, and ethics, right? In that, so why shouldn't AI system be also subject to the same, right? If you are going to use AI system for critical applications like health, transportation, or finance, then you need to be able to do this. So there are some concepts that have emerged. We call it value-inspired neurosymbolic AI. But there are, the concepts that you can read up are human-inspired AI, civilizing AI, constitutional AI, and we have talked about that in a recent article called Neurosymbolic Value-Inspired AI. I think now the time may be running out, so I'm going to wrap up. But there are a broad variety of individual and societal norms, and that there are various value-based objectives that is a norm in the regular society, human society, and there is a quality of service that humans expect. We cannot accept unsafe AI system. We cannot accept operations that are not explainable. Even if they may be right, but you can't explain, you are going to be suspecting, and what if some of it is wrong? So any of all of these come to get brought together, we are going to have to use these laws or guidelines or policies and encode them and ensure that the future systems, which can't be in many cases just generative AI systems, that they can support the kind of things that human society needs and requires. So there is in architecture, I just want to say that on the top right, you see the rules and their knowledge, and then there is innovation both at that level, more of a cognitive level, and the innovation possible at the bottom level, where I said, where we have said brain-inspired memory. So today's neural network architecture is extremely simplistic, but it has also its benefits. Because of that, it is highly scalable, and that is its power. But there's always expressiveness and performance trade-off, and we want to raise the expressiveness also, and hope that performance will catch up, and that will lead to more intelligent systems. So with that, I will end here, and if there are questions, you can see our LinkedIn page, and there are a lot of videos and tutorials and course material on our YouTube, and our project page on Wikisites, and so on and so forth. So with that, let's open up for question or anything else that the organizations wish.
Is there any questions?
I think, Srini, you can unmute all the attendees you want. And so that, is there a question anyone would like to ask Professor Amit?
Yeah. Yes. Hello, sir. Thanks for the talk. So, I mean, it is said that retrieval augmented generation can actually handle a lot of these hallucination problems, right? So, uh, I mean, are they enough, or would neurosymbolic models complement that approach?
So it's like, suppose you have a child, and a child is learning all kinds of wrong things, and then you have a parent or teacher looking after the child and saying the child, don't do this and don't do that, and there is improvement for sure, but it is not the same as giving principle lesson to the child, saying in teaching the child the value, saying this is wrong, and why this is wrong, why if you do this it will be not acceptable, so on and so forth. So RAG is a very good band-aid, and it can do it can prevent some of the problems, and if you don't have principled way to deploy the knowledge and symbolic part of it, that's a stopgap, a good stopgap, but it is not a good solution. RAG, by the way, any of the things that you are doing with prompting and retrieval augmentation and other things, they are quite demanding. It's not coming for free, and so the amount, when we on one hand we value how easy it is to ask ChatGPT some question and get an answer, on the other hand, to develop the RAG and other things, there is quite a bit of effort that has to go in. And then how do you argue about the comprehensiveness? How do you argue about the accuracy and so forth? So yes, you can show improvements. Yes, you can show that you can root out certain problem. Yes, you can direct the AI system. There is a concept called pausing now. There are many other things. We understand that a language model loses out information about what is in the middle. uh, but all of these are kind of band-aid, more or less, of different variety: a small band-aid, large band-aid, and they are not principal way of getting to what we want to. How do you take, for example, the entire legal framework of traffic vehicle and accident related stuff, and apply it uniformly versus using it for RAG? And it's also very expensive. If you're using a OpenAI API, you will see how much it adds up to the cost. So yes, they are interesting things. They are sure we should look at, but they are not necessarily a good long-term solution.
So can we have the best of both worlds? Like, can I somehow incorporate, I mean, for the sake of argument, propositional logic in RAG and make the systems more reliable?
You can, and so there are emerging ways of how to effectively create RAG. There are, how do you use knowledge graph in the process? Yes, they are. The only thing, but then as you see a loosely coupled system versus a tightly coupled system, and in loosely coupled system there will be a lot of communication. So what happens is that the more information you stuff in from your prompt to the language model, the cost, the amount of work that the system does is pretty massive in terms of computation. So it will become quickly very inefficient. Um, so yes, by all means, there are a lot of different things to be done in terms of how do you effectively do the RAG automatically, and or using a particular strategy of going through the knowledge graph and picking up the things, what path to follow. Many interesting things are possible. Sure, those are all interesting things to try. And they will be a good activities in the short term.
Thank you, sir.
Yeah. My question is a follow-up to Aditya's question. I mean, for argument's sake, let's assume that by infusing propositional calculus, we are able to do better. The question is, why would that be? Let's say if it is able to do better, is there a rationale that infusing propositional logic will make it better? Like, for example, like, is there something happening in the lost landscape for which we see hallucination? I mean, this is something that I'm not able to understand.
Yeah. There is I go back to, and I think we need to look at cognitive science and other things in more detail. I go back to a very old paper, very influential paper called "As We May Think" by Dr. Vannevar Bush. It was published in the Atlantic in 1945, and he conjectured up in those days, 1945, a machine called Memex that would be mimicking human brain. And he talked about very interesting concept of trailblazing. He says that the human brain latches onto this to a concept and then traverses in context. And so if you think about in a graph with labeled edges and you are traversing in context, you know exactly why you're going from one thing to another thing. And essentially, it assumes a richer representation. Compare that to what happens here when you take text, break it down in the tokens, and then find all the probabilities, and you build these billions of parameters. And it happens that you have more data on something, you have less data on something. There will be conflicting data. There is no understanding the system has about what is conflicting, what is not conflicting. we should be, this occurrence should get more weight than this occurrence should get weight. Humans, we apply the knowledge that, oh, this is coming from a credible source, I'm going to believe that this is provenance, and I use provenance in deciding what I would take and believe in, what I would not. What I will, even in deciding fake news, for example, say, oh, it came from New York Times by journalists that does ground up investigation. That is a value compared to the same text coming from somewhere else, and that will have different value. We do that. These systems are not able to do that. So because some of the words may have a very tenuous relationship, and the probabilities that they connect them is very weak, this is likely to make system make up the things. The hallucination often occurs because I think that those probabilities are very low between some of those concepts, and then the system still is made in such a way that you take something and create the part of language generation is so good that it makes you believe that, oh, human could have written that. So basically, now we don't know at this stage very well exactly how to combine different kinds of logic or different logic based system themselves have not succeeded too well because they are not scaled too well. So I'm not going to here argue that we're going to use the a prologue or other kind of things, and or any of the other logic systems and the frame logic and this and that. I won't be I won't be able to say that. What we know is that we can use knowledge graph at a very large scale. So I had a web scale a search engine that semantic search engine that use knowledge graph with machine learning, and Google has a web scale semantic search engine that use knowledge graph and this thing. So there is a potential middle ground where you will not get all the formality you want, and still you'll effectively use the knowledge. I think it's some form of only thing I can say is that data alone is not enough, but exactly how you can use the formal systems in combining that, I don't know. I also know that certain kinds of reasoning are very important, very practical. For example, path. Take an example of know your customer application. The company that I had, my second company, had the know your customer deployed at majority of world's 30 largest bank. Where in know your customer, given somebody is trying to open the account, you want to find connection to anything that is known to be a bad actor. And if that is, then you're going to prevent or do investigation. So that is pathfinding, right? This is a very important kind of reasoning that's very practical, and you want to know that. Or causal reasoning. For example, manufacturing line, if errors occur very infrequently in automated manufacturing line, but if it occurs, there is a millions of dollars of expenditure to get the things back in operation. And so there, finding the rare exceptions and what is the cause of that exceptions, this is very critical. What we do is to look at this kind of problem and see how we are going to efficiently achieve that. But on a principled way of embedding logic in this thing, I don't know.
Yeah. Okay. Makes sense. Thanks so much. Are there any other questions from the audience?
I wanted to ask a question.
Sure.
Yeah, Professor Shah, thank you so much for your talk. What I wanted to ask is any such work has been done for medical time series data for anomaly detection? Because this is something that would require knowledge as well as the actual data being analyzed. So
Glad you asked this question. This data, this has been done for manufacturing, smart manufacturing data. So time series, in that data is obviously time series and times, and finding the exceptions, rare events and exceptions for that. We have done that work, and very recently, just last year. We want to, your use case is excellent, and we would love to take that up if we have access to real data or even good simulated data. Please connect with me on LinkedIn, and I'll be more than happy to send you the research we have done on time series data, and finding rare exceptions using neurosymbolic approaches. So maybe that if you have problem, maybe this will give you inspiration. Otherwise, feel free to share with us the kind of data you have, and then if you are interested, you can connect with the team that is working on this and see whether your problem can be also is amenable to further research progress. So yeah, this is very good area to work on. Usually the problem is the lack of data and clear expertise in this kind of thing. If you have this, we'd love to hear more from
I
you.
mean,
thank
yeah.
you
So
so much.
as a follow up to your remark, Professor Amit, I mean, I was wondering what would be in the time series medical anomaly detection would be. I mean, in my mind, I mean, if you look at the breast cancer data, which is like usually available, and at least from Harvard, and some people have worked on these survival window estimation problem, like what is the probability that a cancer patient survives for 5 years, 6 years, so on and so forth. So if you expand that survival window to from 5 years to 10 years, and this is what I have seen firsthand, the moment we expand, the problem becomes a highly imbalanced classification problem between the survivors and not survivors, to the extent that there are only a very few instances, like 2 or 3 cancer survivors among a cohort of 1,800 or so. So I could imagine that's probably an example of a time series anomaly detection in a medical field, probably. I mean,
No,
otherwise,
the more
yeah.
relevant one is something like an ECG, which has a anomaly. So we were looking at ECG
Right,
data
yeah.
and
Mhm,
identifying anomalies. Now
mhm,
it's a fairly complicated thing because you're dealing with the entire heart and the entire human body, but there is expert knowledge in it. So
mhm.
and there are data sets which are reasonably well marked. So this
Right.
would be a big problem where we can sort of
I think this is both of these actually are very interesting observations, and yes, Nina, this is potentially very interesting. We have just started. Our team includes neuroscientists, researchers who do work with neuroscience and AI. And we deal with ECG. We deal with right now we are developing a custom model for cardiology event prediction. So I would really need to, love to learn a bit more about it, and um, happy to, have a call on that. It sounds very interesting.
thank you
In
so
both
much.
these cases, there might be data, and eh, and the knowledge is yes available. Absolutely. In 2005 and 6, I developed a so-called semantic active semantic electronic medical record, and it is deployed and working 24/7. So it is an electronic medical record with three for a cardiology practice, a very large cardiology practice with three ontologies. Ontologies about the cardiology concepts or medical practice concepts, ontology about the business side of it, and ontology about drug and drug interaction part of it. So the third company that I co-founded actually had particular application on cardiology. So basically all I can say is I can vouch that comprehensive cardiology knowledge graph is possible or available. And now if you have maybe we also even have access to some 30, large amount of electronic medical records, but I don't think that includes ECG. So let's see what you have in ECG, and maybe that could be very valuable.
So what we are looking at is capturing ECG using, for example, low-cost sensors. Currently, we can build systems which are low cost. They will even detect the anomalies if you train them in a certain way.
Yes.
But
Yes.
like to go towards the medical side of it, you require something more. You can't just
Yes.
say that there was an anomaly. So
Yeah, and the other thing is that there is all, it's one thing is analogy, but there is, this is part of the whole human system, and other things, what other things are wrong with the body, and what are the other factors also, smoker and BP and diabetes and many other things. So I don't know whether the problem can be simply framed in ECG, or problem requires more holistic data. We just don't know yet. At least I don't know yet. So, but nevertheless, it seems like an opportunity we should investigate. So, yeah, would love to talk about this.
Yeah, I mean,
I'll be in
I
touch.
think probably we can take the discussion in another thread. Are there any other questions from the audience? I think it's getting pretty late for everyone here in India, but if there is none, I would like to express my deepest gratitude to Professor Amit Seth, and I hope it was an excellent talk. I hope we did not wake you up too early for the talk, and thank you so much. We will love to be in touch.
Yes.
And thanks again. Thank you everyone for joining in.
Yeah, glad I could participate. Bye bye.
Bye bye. Bye bye.